Hey, hello everybody. Good afternoon and welcome to the very first session of the Fueling Your Future webinar event series. We're excited to have you all here today, especially our esteemed guests, my colleagues from the Nuclear Innovation Alliance. My name is Mya Zepp, the Nuclear Innovation Coordinator for NIA, and I'll be your moderator for today's session. Before we dive into the content, let me provide you with a brief overview of the Fueling Your Future event series and today's session. Fueling Your Future is a three-part webinar event series for NIB alumni focusing on workforce development in the nuclear energy sector. Today, we will cover introductions to the Nuclear Innovation Alliance, workforce sectors that will be covered in the series, introduction to advanced reactors, and updates on the Nuclear Innovation Bootcamp. Let's start by welcoming NIA's Executive Director, Judi Greenwald. Judi has over 35 years of energy and environmental policy leadership experience in the public and nonprofit sectors, including the U.S. Congress, the White House, the Environmental Protection Agency, the Department of Energy, the Nuclear Regulatory Commission, and the Center for Climate and Energy Solutions. She has focused extensively on decarbonization through the interplay of public policy, technology innovation, human behavior, and markets. I will now turn it over to Judi, who will provide insights into the mission and work of the Nuclear Innovation Alliance.
Thanks so much. Who's moving the slides? Great. So NIA, as many of you know, because you've been working with us through bootcamp, is a think and do tank, and we work to ensure that advanced nuclear energy can be a key part of the climate solution. We identify barriers, we perform analysis, we engage with stakeholders and policymakers, and we nurture entrepreneurship through the Nuclear Innovation Bootcamp, which you've all been part of, and we're hoping that you're going to be even more active in the Nuclear Innovation Bootcamp alumni. We are famous for very geeky reports with very pretty colors, so hopefully you see some sampling of that, and we really try to dive deep, understand the emerging issues that are important for the conditions for success for advanced nuclear energy, and then use that information to inform policymakers and other key stakeholders. Next slide. Great. So what does creating the conditions for success for advanced nuclear energy mean? So the conditions for success, or success in our view, means that we can have advanced nuclear energy at scale, at competitive cost, gets to market, and we have public acceptance. And that means demonstration in the 2020s and commercialization in the 2030s and beyond. So how do we get there? We think we need a whole of society effort from government, civil society, customers, communities, and investors. We think that licensing modernization and public investment facilitates rapid private innovation. So those are things that we spend a lot of time on, making licensing modernization and public investment successful. And we also think we need greater financial sector as well as public investment for global decarbonization at scale. Commercialization is primarily going to depend on success by companies who actually develop these technologies, but we really need everyone to make this a true success. Next slide. So this is our team. Some of us you know, and we've already introduced me. We've also got Patrick White, who's our, actually this has to be updated. He's now our research director. Victor Ibarra Jr. is an analyst. Eric Cothran, also an analyst. Devin Watts is operations manager, and you've met Mya Zepp in our opening. Next. So I'm going to segue now to Devin Watts, our operations manager.
Thank you, Judi, for that information. As a reminder, we do have a Q&A chat open to receive questions that will hold until the Q&A time. If you have any questions for Judi, please feel free to drop them in the chat now. Next, we'll hear about updates on bootcamp and its impact on workforce development from NIA's operations manager, Devin Watts. Devin focuses on planning, program implementation, and operations. Devin comes to NIA with over 20 years of diverse experience, including recruiting, business development, program management, training, process development and delivery for effective and efficient workflow, management of multifunctional groups, customer service, and liaison with internal and external stakeholders.
Thank you, Maya. And good day, everyone. And thank you again for tuning into the first series of our three-part Fueling Your Future series. I've had the pleasure of coordinating the last two bootcamp cohorts and would like to start by sharing some exciting information from NIB 2023 cohort that just ended, which was the sixth edition of the Nuclear Innovation Bootcamp. And you can find the recap on our website through the link provided in this presentation, which will also be shared at the end of the webinar, and we will also share it in the chat for you. Now, the 2023 cohort was the most diverse yet. And so with 16 countries represented, 45% women and 62% of racial ethnic minority. Out of a record-breaking 108 applications received, there were 29 participants that were selected, and including students and early career professionals from all over the world and from a variety of backgrounds. And it was also the first boot camp to be hosted in Asia, in Tokyo, Japan, in partnership with the Tokyo Institute of Technology and the Nuclear Innovator Cultivation Program. And so now we are currently planning for NIB 2024. It's currently in the works, so no information as to where that would be held, but please stay tuned to our social media information for that information once it's released. Now, as you know, the Nuclear Innovation Bootcamp seeks to train students and early career professionals in skills essential in innovation in nuclear energy while executing group projects, with the end goal to increase the pipeline of nuclear energy innovators. Now, from the 2016 to 2019 and 2022 and 2023 NIB cohorts, there's a total of 157 participants that make up the NIB alumni. And in 2023, we here at NIA, we developed a strategy to revamp the NIB alumni for the purpose of increasing engagement, to offer professional and personal support, such as professional networking events and career services, continuing education opportunities, and use of facilities. Now, the NIB alumni was created to provide long-term value by giving alumni the chance to stay in contact and continue to learn from each other along after they have completed the boot camp, which we like to see that many of our alumni are doing that, today. So we just want to, increase that engagement. Now, the NIB alumni goals are: one, to inspire change, to influence, inspire, organize for collective action; and two, authentic leadership, so leading from strengths, sustainability, and equity; and three, network development, weaving a network and building a community through action. And here we have listed our short and long-term needs for the NIB alumni. Now, our communication for the Alumni Association functions is communication will be through newsletters, mailings, directories, etc., to regularly share information about alumni successes and ways in which the platform is benefiting its members as well as the business. Now, this is an opportunity to give alumni follow-ups, spotlights for our alumni, and to see what they're doing now in the world, and share stories about any barriers and how bootcamp has helped address those challenges, whether it be financial, networking, etc., and the reward from it. Now, our communication methods will be through newsletters, postcards, flyers, and to promote special events. So be sure to log into our social media so that you can make sure that you will get that information once we start releasing it. We will also be working on an association directory. So what that will include is industry, company information, as well as alumni information, so that you can continue on that communication with each other. And then, as I stated, our social media will be through our alumni community platforms, LinkedIn, which many of you are members of. And if you're not, please be sure to go over and become a member of our LinkedIn alumni community page. And then also our social networks, as far as Twitter and, I'm sorry, not Twitter, as far as Instagram and Facebook. So be sure that you are members of that to get information. And then as well as email blasts and information from the website. Now, who should join? It's pretty much your participants, speakers, mentors, organizers, co-hosts, and industry sponsors is who we want to join the alumni and who we're reaching out, so you can continue to get a lot of information from these different groups and build our network. Now, as we said, we want to hear from you. So we are working on updating our alumni database, as mentioned, and we need your help. So if you haven't done so already, I know in the summer when we had the pleasure of having Mya as our intern, who's now a permanent employee, by the way, with NIA, but we had the pleasure of her interning with us over the summer, and she sent out an email blast to all of the alumni asking, just to update us as to, where you are now. And so we've gotten some responses, and we like to get a lot more so that we can make sure our records are up to date with the information. And if you have any, spotlights or, anything that you would like to share along your journey, please let us know so that we can share it with our alumni community as well. So if you haven't done so already, click the link below that's in the presentation and provide us with your updated information. Thank you all again for tuning in.
Thank you, Devin, for that information. If you have any questions for Devin, please feel free to drop them in the Q&A chat now. Now let's delve into the fascinating world of advanced reactors. Our last speaker for this series will provide an overview of advanced reactors. First, allow me to introduce Dr. Patrick White, NIA's research director. Patrick leads NIA's research as well as analysis-based stakeholder and policymaker engagement and education. His technical background includes expertise in advanced reactor licensing strategies, regulatory modernization at the NRC, nuclear fuel cycles, and nuclear system safety. Take it away, Patrick.
Great. Thank you so much, Mya. Very excited to be talking with you all today and to really kind of dive into kind of a 201 on advanced reactor technologies. So this is something where I think many of the folks that are NIB alums have some familiarity with advanced reactors, either through their academic studies or through working in this space. And so what I was hoping to do today was really kind of do a deeper dive on some of the technical aspects of reactor concepts that many of you might have seen, but might not necessarily be that familiar with the idea that can help kind of set up some of the discussions that we're going to have later in this series as people start to look at what are potential opportunities for NIB alums in the advanced reactor space. So with that, I always like to start my presentations with a couple of main takeaways. The first one is that I think as folks are starting to look at advanced reactors, one of the things to keep in mind is that it's possible to start to kind of characterize the different advanced reactor concepts that are currently under development by private companies by taking a look at things like their coolant type, their fuel type, and their power output. And these can provide a lot of really interesting insights on things like their safety case and potential economic uses in the future. And that can be one of the really good factors to help you kind of evaluate, is this technology for real, or are there things that this technology is going to have to work through on its path to commercialization? The second is that, and this is something that I think is just really important for the advanced reactor space more broadly, it's that some of the design choices that we're making now for advanced reactor technologies can really help kind of reduce the hazards of nuclear energy moving forward, especially when compared with the conventional large light water reactors that we're using today. And that finally, this characterization and evaluation of advanced reactor concepts and companies is possible by taking a look at their reactor design and the kind of choices they're making with their business plan. And this can hopefully help you get a little bit more information when you're starting to evaluate what are companies that I'm interested in working with, maybe joining, or if you're interested in starting a company of your own in the future, what types of things do you want to make sure you keep in mind so you can start to build a more kind of credible business case for your technology. And so with that, let's go ahead and start jumping into the actual advanced reactors themselves. So the place that I always like to start when I'm talking about any advanced reactor technology or really trying to evaluate any new company in the space is looking at three big things. What's their reactor coolant? What's their reactor fuel? And what's their reactor power output? And these are characteristics that I think can help kind of differentiate the different advantages and challenges of advanced reactor technologies in the space. So while it might just be kind of three kind of bulk characteristics, if you know those and you can learn and you know a little bit about advanced reactor design and operation, then what you're able to do, if you can click one more time, is that you start to get information on things like their safety case, their technology use cases, and what are the business opportunities. Because it's connecting these kind of underlying technical factors to how the reactors themselves might operate in the future. So, for example, if we click forward, let's take a look at how power output might relate to something like the reactor safety case. And so if we kind of think about it, if we started with a microreactor, for example, this is a small modular advanced nuclear reactor, let's say smaller than 30 megawatts electric. Well, one of the things that we're going to know right off the bat with a reactor of that size is that it's going to have a reduced reactor post-shutdown heat load. Essentially, the amount of decay heat that's being produced by that core is going to be orders of magnitude smaller than a large light water reactor, just simply due to its size. And the important implication there is when we're thinking about the safety case of these technologies and their deployment strategies, we're going to have a significantly reduced reliance on reactor heat removal systems. So in conventional large light water reactors, we think of things like having your emergency core cooling system as being a very costly, challenging to engineer system. But with a microreactor, that might not be the case. And so we can start to think, okay, how does this reduced reactor size ultimately feed into maybe a potentially easier path through licensing, maybe a reduced design or safety requirements, or open up maybe different use cases and markets that otherwise wouldn't have been possible for a reactor that had a really large post-shutdown heat load. So what I like to do is kind of dive into each one of these three, the reactor coolant, the reactor fuel form, and the reactor size, and talk about what some of the implications of these might be with some of the major things that are out there and how we can compare it to some of the reactor technologies that are currently operating today. So the first one is going to be the reactor coolant. And really, it affects every part of your reactor, the temperature, size, and the safety characteristics. So in the conventional nuclear reactors we use today, primarily light water, normal H2O. Conventional water, despite maybe not being the flashiest coolant, is really nice for two main reasons. One, we know a lot about water. We've got really, really well-characterized properties, and we have a lot of engineering experience with high-pressure water systems. We've been using it for over 100 years. We know how to design and build these. That being said, there are a few challenges with it. One, it's got a very low boiling point, needs to be operated at high pressure, so that creates some mechanical system challenges and some safety system challenges. It's got a low energy storage capacity, and by that I mean, if you start to heat up water, it very quickly can vaporize and boil, change phase, and then that introduces some design and operational challenges. And finally, water can be reactive under some conditions. If you take certain metals and you start to heat them up, you can have oxidation reactions where the oxygen is literally split off your light water coolant and produces hydrogen gas, which introduces some additional challenges. Also, water likes to eat through things, so it's something you have to design for. As we start looking to advanced nuclear reactors moving forward, we now start to kind of open up the space of what are different reactor coolants that we could use. And the important thing to think about is how might these different coolants start to provide us kind of changes to things like the operating temperatures. Can we operate at higher temperatures? The reactor size, and what the potential safety characteristics are. And so now we're going to dive into kind of each one of these four major advanced reactor coolants, molten salts, gas coolants, liquid metal, and heat pipe, and talk about what some of the implications might be. So the first one that we'll talk about is molten salts. And for the purpose of this conversation, we're really going to limit it to solid fueled, liquid cooled reactors. So when I talk about molten salts here, I'm specifically talking about the coolants and not actually about reactors that might dissolve the fuel in their coolant. We can talk about those in the Q&A afterwards. But one of the really big things when you take a look at molten salts from the outset is that they're a fantastic coolant because they've got an extremely high boiling point, can operate at low pressure, have very high heat transfer, and can retain radionuclides. And so these come with three major advantages. You basically end up with a coolant that can absorb a lot of heat, won't boil, and so if you have an accident or if you have some condition where you lose the ability to cool the reactor, that coolant can absorb a lot of that thermal energy from decay heat. And finally, it retains radionuclides. So if you do have a fuel that potentially suffers a failure or leaks radioactive material, those radionuclides that might normally be released to the reactor system in a light water reactor can actually be chemically bound by the salts that you have. In this case, two of the example of salts that we talk about are FLiBe, which is a fluoride lithium beryllium salt, or FLiNaC, which is a fluoride lithium sodium potassium salt. And so these chemical properties become a huge advantage for molten salt reactors moving forward. That being said, molten salts do have some downsides. For example, the first is that we have a lot less experience operating large industrial systems that use these types of molten salts. They come with increased corrosion and chemical hazards, and this can ultimately make the systems harder to engineer and maintain. And so these are kind of interesting challenges and drawbacks as you're thinking about trying to deploy molten salt reactor technology. yes, it might have some advantages on the coolant. It might allow you to design a nice, compact nuclear reactor, but you're going to have a lot more questions related to the qualification, the design, the prototype, and the long-term operation of your systems. So one example of the reactor technology that's using this is Kairos Power. So Kairos Power is using a liquid fluoride lithium beryllium, that FLiBe salt, to help cool its Hermes test reactor. And so this enables a very small, compact nuclear reactor and a very excellent safety case in the idea that it can help kind of prevent the release of radioactive material in any accident situation. But what Kairos is having to do is undergo additional testing through non-nuclear and nuclear prototypes to try to provide validation on their essentially system design, because we don't have that much experience with the coolant, and then also on the longer term operation. So we understand that this reactor could operate not just for a couple of months, but for a couple of decades safely. And so Kairos Power is being very deliberate with their testing strategy to help overcome these challenges associated with using FLiBe coolants. We can head to the next slide. So the next kind of major advanced reactor coolant that we're seeing described is gases. And so the most common gas that we'll have is helium. There's a long experience with operating nuclear reactors with helium, and there are a couple of major advantages of this. First, no boiling concerns. In conventional light water reactors, we're really worried about what happens when your water coolant boils, because it changes the heat capacity, it changes the heat transfer, and it can change the way that the system is interacting with the fuel. If you have a gas reactor, no need to worry about it. It's already gas and it will always be gas. It's incredibly well characterized. There's a lot of experience using helium gas systems, and it's incredibly non-reactive gas. It's the joy of being one of the noble gases over on the right side of the periodic table. It's not going to react with anything. And we have a lot of experience using helium gas. Specifically, there was the Fort St. Vrain nuclear reactor that was operated in Colorado in the 1970s and 1980s in the United States. And that was actually a high temperature gas reactor that was operated with helium. So we have modern experience in the United States using these systems. That being said, it also has some drawbacks. The first is that just running gas over nuclear fuel really is not that efficient for heat transfer, and it has an extremely low energy storage capacity. If you start to heat up gas, the temperature will increase dramatically based on the volume and mass of gas that you have. And so what that means is that you can't rely on that gas to help kind of absorb that heat that might be released if you lose the ability to cool the reactor. And so you have to start to think about how can you design your system differently so it doesn't necessarily rely on the properties of the coolant to ensure safety under all conditions. So an example of this is the X-Energy reactor. So X-Energy, specifically their XE100 reactor, is a helium-cooled gas reactor. And so in this case, they run helium coolant over their nuclear fuel, and that's when it's going to be able to remove the heat. The other advantage is that gases can, because they don't have a boiling point, can operate at extremely high temperatures without the worry about corrosion. So let's go to the next coolant. So liquid metal, this is a really interesting one. So what we can look at here is that we're, instead of running, again, liquids or salts or gases, we're actually taking liquid sodium in most cases and running that over our nuclear fuel to remove the heat. And so the advantage of liquid sodium is that it has an extremely high boiling point, thousands of degrees C. It has excellent heat transfer, and it has very high energy storage capacity. So that sodium can absorb a lot of thermal energy, which makes it both efficient for designing a reactor, but also means that if you have a reactor power transient, if you have changes in your core power level, or you lose the ability to cool the reactor following shutdown, that coolant can absorb a lot of that energy without having huge changes in temperature. So it becomes a really interesting safety characteristic. It also allows you to build a very tight and small reactor. We have some engineering operating experience with this. The US has operated a number of sodium fast reactors, and there have been a number around the world. So we have some experience. The main challenges are the coolant is reactive. So if anyone has ever had any knowledge of looking at sodium-based systems, what happens with liquid sodium when it comes into contact with water? Everything catches fire, and sometimes it explodes. And so when you have a highly reactive coolant, you have to start to think about how can you safely design this system to prevent any types of those interactions and mitigate them if they do occur. And so this can make your systems a bit harder to engineer and harder to maintain. And you have to think about the interfaces between your systems that are using a liquid sodium coolant and the rest of your plant. For example, you might not want a power plant that directly interacts a water balance of plant or steam cycle with a liquid sodium interface, because the steam generator between liquid sodium and liquid water would just be asking for trouble. And so there have been different proposals on how to kind of get around this. And one of the companies that's looking at using this liquid sodium coolant is TerraPower. And so TerraPower, with their natrium reactor, is looking at doing a liquid sodium cooled fast reactor. And so in this case, what they're doing is they're running liquid sodium over their core and then having it interface directly with a molten salt energy storage system. And so because the liquid sodium is so effective at transferring that heat and storing that heat, it becomes a highly desirable interface with that molten salt storage system. So it becomes a really good fit as a way to try to absorb heat, store it, and use it later. And we'll talk a little bit later about how that fits into kind of what TerraPower's design regime is. And finally, the last one is heat pipes. And this is a little bit of an interesting one, where instead of having liquid coolant removing the thermal energy from our fuel, we're looking at using solid components called heat pipes. And so a heat pipe is essentially a long sealed tube that uses an intermediate fluid to essentially help kind of move heat along the length of the tube. And so you can imagine at one end, you are either boiling, vaporizing, or otherwise changing state of your kind of sealed working fluid. The working fluid then travels via pressure differential down to the cold end, where it then either condenses, cools, or otherwise changes state and transfers that thermal energy. And so you basically end up with a way to move heat efficiently from one place to another without the need for having large amounts of flowing liquid or gas. And so this can be a really good advantage because it can operate at a higher operating temperature. There's no moving coolant, so you don't have to worry about your loss of coolant accident. You have multiple reactor heat transfer paths. So instead of relying on one giant tube that's moving all your coolant, you instead would have a large number of these small heat pipes that are moving the energy. So the failure of one isn't going to lead to kind of a catastrophic challenge to the reactor. And finally, you eliminate a lot of the corrosion concerns. You don't have to worry about what happens when that liquid water or sodium or salt flows over your pipes. It's just one sealed unit that you're looking at. The challenges of those, however, is that heat pipes are going to be a lot less efficient, at least in their current form, than heat transfer with liquid coolants. And that's just because ultimately you're moving a lot less material and you can move a lot less thermal energy. We also have more limited operating experience with these technologies. And so it's not necessarily clear how they're going to operate over long periods of time or in some radiation environments. That being said, for all these advantages, there are a number of companies that are looking at it. So for example, if we take a look at Westinghouse, they're looking at using the heat pipes as the basis for their Vinci reactor. They have a solid core that they then use heat pipes to remove that thermal energy from and transfer it to a balance of plant. And so the idea is that it can create a very compact and simple design that doesn't necessarily require the pumps and valves and fluid control systems that you would historically have in a commercial nuclear reactor. And so it's one of these really interesting things that's maybe pushing them to a slightly more novel design. That being said, with heat pipes, they're never really going to be designed, at least in their current state, at moving large amounts of energy. So I doubt you'd have a reactor that would be a 1,000 megawatt reactor that use heat pipes. Right now, they're intended for much, much smaller designs. And so with that, let's move to the next category, which is looking at reactor fuel. Again, reactor fuel, much like a coolant, can have a huge impact on what temperatures you can operate at, what are the economics, and what are the safety characteristics. So for the reactors that we use today, we use ceramic low-enriched uranium in a form of UO2. And with this existing fuel form, it's really well characterized, it's a fairly stable fuel form, and it's easy to manufacture. We understand how this fuel behaves under a wide range of conditions. Challenges? Well, it's got really poor heat transfer. With any type of ceramic, you end up with a low coefficient of heat transfer. And so you basically end up with large temperature gradients that occur over the fuel. This can lead to a lot of stresses and cracking within the fuel and potentially allow for the release of some radionuclides. Additionally, these types of fuels require metallic cladding because you couldn't have an interface between the uranium oxide and the water coolant in existing reactors. And so this metallic cladding layer then becomes a potential opportunity for corrosion, for surface interactions, and it becomes something you have to manage. So it's not necessarily desirable. As we start looking at advanced reactors, we now start to kind of open up the space and say, what are different ways that we could have physical fuel forms? And what might some of the advantages be? And so for this presentation, we're just going to touch on the top two, specifically the metallic fuels and the triso fuels, but happy to answer advantages later about some of the molten salt fuels and the carbide fuels. So the first one that we'll talk about are metallic fuels. And so with a metallic fuel, instead of using a uranium oxide, a ceramic, what we're interested in doing is using a uranium alloy, like a uranium zirconium alloy. And so these metallic fuels have a couple of major advantages. First, because you can essentially have better heat transfer across your fuel, it can lower that reactor center line temperature and allow you to operate your fuel at a net higher power than you would with a uranium fuel. You can imagine one of the challenges in a oxide-based reactor, in the conventional reactor, is that if you've got a multi-100-degree temperature differential between the surface of your fuel and the center of your fuel, you're trying your best not to melt that fuel. In a metallic fuel, there's an opportunity to operate it at a net higher temperature and kind of achieve an overall higher thermal efficiency for your system. And so these metallic fuels can potentially bring a lot of advantages. And we do have some operating and engineering experience using these. The challenges, however, is that the operation of these fuels under a wide range of conditions hasn't been fully characterized. We have thousands of reactor years of experience using oxide fuels, and we understand how they behave under a wide range of conditions. These metallic fuels, however, we haven't necessarily put through the same level of testing. And so there's some question about if you left this fuel in a reactor for a period of years or maybe even decades, in some designs that have kind of life of core or life of plant cores, how are these fuels going to behave? And so it's a question that we're still working through. And so these uranium fuels become a really interesting opportunity because they also enable the use of more fast reactor technology. And so this is one, again, we can talk about later about the difference between thermal spectrum reactors and fast spectrum reactors if folks are interested. But the idea is it potentially opens up kind of a new regime for thinking about the operation of your fuel under a wider range of conditions. So again, this metallic fuel fits really well with TerraPower's design, where they're interested in using that sodium coolant. Because the sodium coolant would ultimately match very well with the metallic fuel and would have a lot of the similar operating characteristics. So it's something where you can kind of see it becomes a bit of a natural fit there for them. The next type of fuel I want to hit on are TRISO fuels. And so these are a really, really interesting technology where what they do is they take small particles of uranium oxide and then coat it in layers of carbon and silicon carbide. And so TRISO is actually an acronym for tri-structural isotropic fuels because it describes that little uranium kernel wrapped in layers of protection. And so what this fuel does is it has a high level of stability, excellent radionuclide retention, and some proliferation resistance. Essentially, that little particle is stable at incredibly high temperatures. It helps capture any types of radionuclides that would be released during the fission process because the radionuclides would have to make it through those multiple layers of protection before they even exited the fuel kernel. And it's proliferation resistant because you have to do a lot more physical and chemical work to try to extract any special nuclear material that might be in the fuel. And so this becomes a really interesting opportunity to say, hey, how do these TRISO fuels potentially fit into something that is a high temperature, high safety application? The downside of TRISO fuels, however, is that it's a much more challenging fuel production process. Rather than taking a uranium oxide and squishing it into a pellet, you have to think about how to make sure that every single one of your particles have the exact same layers and that you understand what the constraints and limitations are on that engineering process. So there's been a lot of work to try to develop TRISO fuels, and they end up being the basis for a lot of different reactor technologies. So for example, if we take a look at the X-energy reactor, they've selected the TRISO fuel as something that makes sense for them. Because the helium in the X-energy reactor can go to extremely high temperatures, they've selected a fuel that is also stable to really high temperatures. So it allows them to kind of achieve a much better economic condition for their reactor because they can operate at higher temperatures that lead to higher efficiencies and other potential industrial use cases. And so you can see here, there's kind of a natural synergy between what they wanted to select for their coolant and what fuel they're using, so that they line up in the best possible way. The last thing that we'll talk about before we kind of do a few examples of how these things all fit together is reactor power. And reactor power is absolutely critical because ultimately it's going to affect the physical size of the reactor, the construction opportunities, siting, and some of the different safety characteristics. So when we talk about conventional nuclear energy in the United States and largely around the world, we're generally talking about very large reactors. These reactors are many hundreds of megawatts, and most of the times are over about 1,000 megawatts electric. And so with that, it comes with a few kind of challenges related to the size. If we start talking about advanced nuclear, we start seeing them being operated in a much wider range. We might have large reactors, 300 to maybe 1,000 megawatts. The small modular reactors, maybe 30 megawatts to 300 megawatts. And then finally, microreactors, things lower than 30 megawatts. And so you can see we're really kind of spanning about 4 orders of magnitude here in terms of your power output. Now, this reactor core power is really important for a number of reasons. One, it's going to affect the physical size of your system. You can imagine the footprint and the amount of nuclear fuel that you're going to need for a small microreactor is going to be very different than a reactor that's producing 100 times or more the amount of power. Second, as you start to decrease your reactor power, you start to reduce a lot of things related to safety, specifically the amount of actual radioactive material that's in the core that could be released during an accident, the amount of thermal energy that's going to be released from radioactive decay following shutdown, and the amount of energy that potentially could be released in an accident. And so what this means is that the safety systems and safety requirements we have for very large reactors to help accommodate things like how to ensure the reactor fuel stays cool after shutdown might not be issues for smaller reactors. You might be able to use things like convection, conduction, or radiation to try to remove the thermal energy without the need to have forced convection from backup pumps or other backup systems. Additionally, if you're starting to look at siting, well, the worst case release from a very small reactor is probably going to be a much, much smaller potential impact on the community than a reactor that's 50, 100, 200, 500 times larger. And so this creates a really interesting paradigm where you can start to think, okay, does change in the reactor size potentially change the siting requirements? And could we integrate nuclear into places where otherwise we would be concerned about what the footprint for safety would be? And so you can see this is kind of the final piece that if you start to understand, you start to get an idea of what this reactor is actually being designed for. And we can talk a little bit about later on some of the impacts on reactor size. So finally, I think you hopefully can start to see how if you start to understand some of these reactor characteristics, like the coolant, the fuel, and the power output, it starts to give you more insights into how the reactor is going to operate. So let's dive into a couple of examples. So the first one is, we've already talked a little bit about them, X-Energy's XC100. So here, if we kind of go down those 3 characteristics, we can take a look and say it's a gas-cooled, TRISO-fueled, small modular reactor. And what that starts to tell us is, okay, they select TRISO fuel and gas-cooled and SMR, which means that, hey, it's going to be a smaller reactor that can operate at a higher temperature that's got an excellent safety case. And so you can start to see now, okay, what they're really going to be aligning for is places where they might have a need for really high temperature heat. They have a very high expectation of safety, and the deployment of smaller units might match up with it. And that starts to kind of point you to why X-Energy is really looking at the industrial heat market as a potential path forward for their technology. In their partnership with Dow Chemical, specifically looking at deploying the X-Energy at the Seadrift site in Texas, this type of reactor would line up really well with the needs of a chemical producer who want high reliability, high temperature process heat, that want to be able to deploy it based on how their demand is changing at their site, and want to ensure that it's a very safe reactor that matches up with the safety characteristics of the plant. They don't want to introduce a new energy source at a chemical facility that's ultimately going to raise the hazard profile of the facility. So you can see here now how these 3 pieces start to play together, and you can kind of understand why X-Energy is targeting the markets they are. Let's go to the next slide. So Natrium, we've got a slightly different approach. They've gone for the sodium-cooled, metal-fueled, and large reactor. And so what you're looking at here is you now have a technology where they can operate at high temperature consistently. It can operate at a high power because it's got that combination of the really efficient sodium coolant and the really effective metallic fuel. And it's something that can store a lot of thermal energy and integrate well and efficiently with energy storage systems. And so what they've done is they've now created a system that's more optimized for kind of long-term energy production. And so they've got a really high reactor heat core capacity. They've got reduced shutdown requirements because the reactor can survive a lot of different power variations while remaining in a stable state. It can integrate really effectively with large amounts of thermal energy storage. And so you now see why TerraPower, with their Natrium design, is looking at kind of pursuing markets, specifically with their Kemmerer, Wyoming project, to integrate into more variable energy production. Because now you have something that can really kind of match grid conditions and provide energy on demand when it's needed, and use that thermal energy storage system to help kind of balance fluctuations that you see in the grid. And it's a very different market than what X Energy is going for. And a lot of that ultimately drives out from the technology they've selected. If we can go to the next slide. Kind of the third example is if we take a look at Kairos Power with their Kairos Power FHR, it's a salt-cooled, TRISO-fueled small modular reactor. Again, here they've selected an interesting set of combinations. By using the salt-cooled and the TRISO-fueled, they've designed a reactor that's going to be extremely effective at retaining radionuclides. So even under accident conditions, one, the TRISO fuel is going to be a really effective barrier to any types of release of radioactive material. And then the coolant they've selected is almost a secondary barrier for trying to retain it. And that means that they're potentially going to have a much lower reliance on their reactor containment systems, which could ultimately help kind of reduce the cost of these systems because they've got multiple independent barriers to release radioactive material. By using a small modular reactor, it's kind of an additional fact where they're lowering the amount of material available for release. So this this Kairos Power design ultimately becomes an incredibly safe reactor, has the potential to become an incredibly safe reactor because of this combination of factors that they've used. And then the question would be, how does that ultimately integrate in a commercial sense with power production or other industrial heat needs? The final example that we'll look at is the Aurora Powerhouse. And so this is a really interesting heat pipe cooled, metal fueled microreactor. And so with the Aurora Powerhouse, they really selected a technology and a set of choices that tries to kind of eliminate the safety risk and create the minimum viable kind of nuclear power plant. By using a metallic fuel, they have a fuel that's stable to fairly high temperatures and very effective at moving heat. They've got heat pipes, which eliminate any type of loss of coolant accident and help kind of reduce the potential opportunities for accident scenarios. And by using an incredibly small reactor, the amount of decay heat that they would have to remove is minimal. Oftentimes I've heard the amount of decay heat from the Oklo Aurora Powerhouse as being similar to a lawnmower, a standard gas lawnmower. Incredibly small amount of energy. And so this creates an opportunity for them to have an incredibly safe reactor with a very small footprint that hopefully would have regulatory requirements that would match it. And it could be a highly modularized life of reactor core that they could then use to kind of power a device and then remove the core when it's completed. And so this creates kind of a very different paradigm of a rapidly deployable, very small footprint nuclear technology for a specific application. Again, you wouldn't power a large chemical facility with an Aurora Powerhouse, but it's interesting to figure out how it could be a specialty source of power in certain high-use applications. And so that really kind of brings us back to this kind of high level of takeaways. Really talking about how kind of a deep dive on advanced reactor technologies can provide really important insights on kind of what the goal of the technology is, what the potential use cases are, and what the safety case might be for regulation and technology development moving forward. A lot of these things just kind of become the starting point for talking with different companies and saying, okay, what specific things are they looking at, and how does that ultimately affect what the applications of this reactor technology might be? We can talk a lot about things like siting, about economics, about costs and deployment, but those might all be things for the Advanced Reactor 301 or kind of the next conversation we have. Hopefully this is kind of a great starting point as you start to look at different advanced reactor companies in the space and try to evaluate what might be the right steps for you moving forward. So with that, I would love to turn it back over to Mya and we can have some conversations. Actually, let's go back one slide. We'll just hang out on the takeaways as we're doing Q&A for the next few minutes. So Mya, I'll turn it back to you.
Thank you, Patrick, and thank you to all of our speakers for those insightful presentations. Now we want to hear from you, our NIB alumni. Feel free to submit your questions using the Q&A chat, and we'll do our best to address as many as we can in the time provided. We will start now with our first question, which is for Judi. What are the current challenges for licensing modernization? How do we incentivize the financial and public sector's investment in advanced nuclear energy?
Thanks. I actually think I'll let Patrick take the one on the challenges to licensing modernization, and then I'll answer the financial question one. So go ahead, Patrick.
Yeah, happy to. So when it comes to licensing modernization, the big question is how can we ensure that the regulator is ready to look at all these different reactor technologies that differ significantly from the reactors that we have today? The reactors, these large light water reactors, the regulatory system has largely been optimized for it. And so it's asking how can we have the NRC think in kind of a more risk-informed, technology-inclusive, performance-based way about reactor safety so they can evaluate technologies on a case-by-case basis and create a more predictable and efficient regulatory system moving forward. And so that's kind of being done on 3 timescales. On the first timescale, it's working with the NRC staff to try to figure out, hey, what are the questions that you have in the near term that you need to address to license kind of the first of a kind reactors we have coming through the licensing process, much like the Oklo, X Energy, Kairos, and TerraPower examples that we use. The next step would then be saying, what do we need to do kind of in the midterm as we start looking at deployment of advanced reactors in the early 2030s to late 2030s? How do we create a new regulatory system that can enable that type of innovation? And that's what we're seeing with the NRC's work on something called 10 CFR Part 53, or the Advanced Reactor Regulatory Framework. And the final one is trying to think kind of long-term, how do we create a regulator that ultimately enables the deployment of nuclear energy at scale? And I'll ask everyone to get back to me on that. It's an interesting work stream that NIA has going. We'll be working on it over the course of the next year. And Judi, I'll turn it over to you on the economics.
Great. So there are different approaches to this in different countries, but in the United States, which is where we focus, generally getting more investment in these early stages of commercialization for advanced nuclear energy, and in fact for technologies in general, requires a partnership between the public and private sectors. We have a very strong entrepreneurial culture. In particular, there's a emerging strong entrepreneurial culture in the advanced nuclear energy world, and that's really important for generating ideas and we're doing a lot of the heavy lifting to get to the point where we commercialize technologies. But these early commercialization efforts also need public support because it's very difficult to get over the hump to commercialization when there's so many public benefits. And you want to make sure that early movers aren't disadvantaged by they're the ones who go first, but then others who are fast followers potentially or longer followers might be able to reap those benefits. So we have a number of things that we do here. We have public-private partnerships through something called the Advanced Reactor Deployment Demonstration Program, which is a big DOE program, which has been generously funded over the past few years. And we have several projects that are moving ahead under that, and it's a shared investment between the public and private sector, and it's going to have benefits for the entire ecosystem of advanced reactor commercialization. And we also have several tax credits that were recently enacted under the Inflation Reduction Act, and these are different types of tax credits. Probably the most important of them are these technology and neutral clean electricity tax credits, for which advanced nuclear energy is eligible. And it's a very important option. You can take either a production tax credit or an investment tax credit, depending on your situation and your business model. And those are going to incentivize private investors to be able to put their own money on the line and to potentially earn money, but also to have public support so that you can buy down the risk for these early mover projects.
Thank you, Judi. Thank you, Patrick. The next question is, why is fusion not discussed within NIA reports and activities? Why is the focus on fission?
Yeah, it's a great question. So I think a lot of it comes down to kind of where do we see technology deployment going in the near term and what do we think is kind of slightly farther off. And so I think kind of based on the commercial readiness of different technologies, we really see fission as being something that's going to happen first, and then fusion is going to come afterwards. In the course of the last 3 to 5 years, we've seen immense growth and interest, specifically from private companies, in development and deployment of fusion technology. But we're still a few years off from seeing kind of commercial scale deployment of fusion energy. We still need to see commercial break even, or essentially more energy out than in from fusion reactions, before we can start talking about the specific role of fusion energy in future electricity grids. That being said, NIA is partnering with Clean Air Task Force on some early work to think about how do we set up the conditions for success for fusion energy moving forward. And so that's something that we'll be really interested in kind of tracking over the course of the next couple of years and trying to make sure that we can create a condition where if private companies are ready to demonstrate their technology, we can figure out what their pathway to deployment looks like.
Thank you. The next question is, why is withstanding power transient an important reactor design choice, i.e., what is the fundamental trade-off?
Yeah, so with reactor power transients, it really comes down to the stability of your system for kind of a wide range of different operating conditions. One of the challenges that you have is that while you like to think that you can operate your reactor at 100% power under all conditions, there are a lot of things that potentially can change what power level your reactor is operating at. Do you have changes in how your coolant system is working? Do you have changes in your reactor control system? And so you'll end up with kind of different fluctuations that occur in your power plant throughout the course of normal operations and during accident conditions. One of the things that you're really interested in from a safety and design point of view is that you want a reactor that operates at a nice stable equilibrium as opposed to a reactor that's hovering right at an unstable equilibrium. So in the United States, for example, one of the factors that we'll look at is something called the reactivity coefficient. So this is getting definitely into the technical weeds, but the idea is that US reactors are required by law to operate at kind of a stable valley point, where if the reactor starts to heat up too much and the power starts to increase, physical feedback mechanisms will cause the reactor to want to drop in power level and return back to a stable point. Reactors that have a positive reactivity coefficient essentially operate at the top of an unstable equilibria, that if the reactor starts to heat up or increase in power, it will want to continue to increase in power. And so the idea of creating a system that can operate under very, very stable conditions and survive power transients is really helpful from an operational point of view. It makes the reactor easier to operate and gives you more margin to ensure that you're in a kind of a safe, usable condition, and also helps ensure that the reactor is going to stay in a safe condition under all possible accident scenarios. And that's something that would come across during the licensing process with whatever your national regulator is.
Thank you, Patrick. We have time for one more question. How is proliferation resistance quantified and measured across different fuel technologies for comparison?
It is a great question, and it's something that I think is still an ongoing source of debate in the non-proliferation community internationally. One of the challenges with nuclear technology in general is that a lot of it is, by its nature, a bit of a dual-use technology. If you are producing plutonium inside of a commercial nuclear reactor, which you do just through the transmutation of uranium-238 into plutonium-239, you need to think about how that material is being accounted for and secured throughout the kind of nuclear supply chain. One of the first things that you'll talk about is how easy it would be to extract that material and purify it into something that a bad actor could use to essentially support proliferation of nuclear weapons. So certain fuel forms, such as liquid-fueled reactors, may be a bit harder to ensure that you understand where every single gram of special nuclear material is in your system, versus a traditional kind of light water reactor where you can do things as simple as count the number of fuel pins or count the number of fuel assemblies to have some idea of where that material is at all times. And so a couple of things you'll look at are essentially how easy is it to track the fuel, and then how easy would it be to extract that special nuclear material from the fuel if you want to purify it and use it for other applications. That being said, I think this is something where it comes down more to kind of expert judgment and discussion among different folks that are knowledgeable in the space, as opposed to kind of a strict numeric metric that we can use. Because this also turns a little bit into how do you think about security and safeguards, which is more of a theoretical activity than something that we have kind of a firm numeric basis on. But it's definitely a really interesting question as we think about trying to deploy nuclear technology to countries that don't currently have nuclear weapons, and that we want to try to limit their access to or opportunities for diversion of special nuclear material for those purposes. So it'll be an ongoing discussion, I think, over the next few years as we think about what role nuclear energy can play really in global decarbonization, and not just in terms of decarbonization in existing nuclear states.
Thank you for that, Patrick. Well, as they say, time flies when you're having fun. So as we wrap up this session, I want to express our gratitude to Judi Greenwald, Devin Watts, and Patrick White for sharing their expertise with us today. Remember, this is just the beginning of our Fueling Your Future series, so be sure to tune in for the exciting upcoming sessions that we have planned on November 28th and December 13th. Thank you all for joining us. We look forward to...
Maya, there was one last question in the chat. Do you mind if I hit it? Because it's a great one. Sorry to throw off your vibe, but I always love these great questions. So the final one that came in was, is the NRC interested in harmonizing its standards with other international regulatory authorities so that US reactor designs could be more easily licensed abroad? I think this is a really interesting question moving forward because, again, we don't want just a nuclear reactor that powers the United States. We want nuclear reactors that can power the world. And so one of the challenges is that nuclear regulation is ultimately kind of a nation-specific question. Countries retain their kind of national authority to determine what can be built in their country. And different countries have different philosophies when it comes to nuclear regulation. And so one of the things we have to think about is how do we create a standard where all the countries can agree on general principles, and then allow for essentially the national specific interpretation of those principles. So it's a really hard question. Unfortunately, I don't have a great answer for you on it, but I think it is something that the NRC and other regulators are looking at because they recognize that there are a lot of really, really good opportunities to have a reactor technology that can be licensed in one country and accepted everywhere. But there are specific issues that we're going to have to work through to try to determine what makes sense and what's kind of a uniform set of standards that we can use around the world. Sorry, Maya, hate to throw off your conclusion there, but it was a great question I wanted to make sure we addressed.
Yeah,
So
and I'm
before-
going to make it worse. I'll just add one other thing. So sometimes people, when they say harmonization, they mean that every country would have the same standards. I doubt we'll get there because countries have interest in keeping their sovereignty in this space. But I think we could wind up in a situation where countries would be more likely to accept licensing that has been achieved in another country. So it's a mutual recognition of others' efforts. So I think that that's probably an easier lift. Sometimes people might refer to that by harmonization, but sometimes not.
Hey, well, before Patrick threw off my vibe, I was saying thank you all for joining us, and we look forward to continuing this journey of exploration and learning together. Have a great day.